Chapter 2, Lesson 1 of Precalculus. We're going to wrap this lesson up by looking at the applications of quadratics. We talked about the vertex form of quadratics, and I do want to cover one more thing about that, and how do we get a quadratic into vertex form. In the last video we looked at these values where finding the a comes from standard form, the h from the opposite of b over 2a, and the k from c minus ah squared. There is another way that we can use to get a standard form equation into vertex form, and that is by completing the square. Completing the square we did earlier this year, so I'll run through it very quickly, and a couple of reminders before I do an example. In order to complete the square, the leading coefficient, that a term, has to be a 1. If it's not a 1, then we're going to need to divide the x terms by that coefficient in order to make that 1. The constant, if you remember from completing the square earlier this year, we kicked over to the other side of the equal sign. Well, in this exercise, we're not going to have an equal sign, so we're not going to kick it to the other side. We're just going to kick it outside the parentheses. So we're only going to divide the numbers in the parentheses by that coefficient. We're then going to add b over 2 squared inside the parentheses, and then to balance that off, because we put something there that wasn't before and we have to keep the expression equal to what we started with, to balance that off, we're going to add the opposite of that on the outside of the parentheses. But I do have to multiply in the parentheses by any number that's in front. This is that coefficient that we factored out. So what I add outside is actually a times that b over 2 value that I added in the inside. And again, that probably sounds confusing, but when I show you an example, hopefully that'll make sense. And then we go ahead and factor the inside parentheses, which is now a perfect square, thus completing the square and putting the expression in vertex form. All right, so let me walk you through an example, show you how that works real quickly. We notice that the coefficient here is a 3. It has to be a 1 before I can complete the square. So the first thing I'm going to do is I'm going to factor that out of these two x terms. Basically, I'm going to divide both of these by the 3, and I'm going to kick the 11 outside. Okay, the constant goes outside. I divided this term by 3 and this term by 3. Now notice, this is still the exact same thing that I had before. 3 times x will give me 3x squared. 3 times 4x will give me 12x, and then I still have the 11. So I haven't changed anything yet. But now I got to take the opposite, not the opposite. I'm going to take this b term, which is 4, divide it by 2, and square it. So I'm going to add 4 into the equation here. Now I added 4 in here, but remember, everything in the parentheses is being multiplied by this 3. So while I added 4 on the inside, in order to balance off what I just did, I need to subtract that same value from on the outside. But I have to remember that this 3 is going to be multiplied this, so this 3 times 4 is a 12. So in order to balance that off, I add the opposite of that on the outside. So that's where this comes from. It's the a, which is the number out here, times the number I put in here. That's what goes out here, the opposite of that. All right, now that I have that, I can simplify the expression by factoring this, because now it's a perfect square. I factor it, and then I simplify these terms out. So now I have it's in vertex form, a times the quantity x minus h squared plus k. So by completing the square, I can I can put this in vertex form by doing it that way. So let me do a couple of examples for you. Here the coefficient is a 1, so I'm simply going to put that term and this term in parentheses. I'm going to kick the 6 outside, and then I'm going to complete the square. So half of 4 is 2, 2 squared is 4, so I'm going to add 4 in here. Because I added 4 on the inside, I need to balance by taking 4 on the outside. I now have a perfect square, so I simply factor this, x minus 2 squared. I simplify out here, so now I'm in vertex form. My a value is a 1. It's a horizontal shift to the right 2 and a vertical shift of up 2, and my vertex would be 2, 2. So putting it in vertex form using standard form is a lot quicker and a lot easier than going through that whole opposite of b over 2a and then c minus a h squared. But we have to know these different ways to do things. All right, let me do another one for you. Now here there is a 2 in front, so that cannot be there before I complete the square, so I need to factor it out. So I'm going to divide both this term and the bx term by 2, and I'm going to kick the constant outside. Now I'm going to complete the square. So I take half of 3, which is 3 halves, and I square it. So that's going to be 9 halves. So I'm going to add 9 halves into the expression here. Now I need to add the opposite outside, but I have to multiply this 9 halves by this term that's in front. So 9 halves times 2, I'll do that out here for you real quick. 9 halves times 2, the 2's reduced, that's going to be 9, so I'm just going to subtract the 9 out here. So now that I have my perfect square, I can go ahead and factor the inside, and that's going to be what I squared to get that, squared minus 2. So this is the vertex form of this expression here. All right, and let me do one more. So here I have 5 minus 25x squared, or 5x squared minus 25x plus 12. Again, this is not a coefficient of 1, so I need to factor that out. So I'm going to do that for both of the terms that have an x. And I'm going to kick the constant outside. All right, then I go ahead and complete the square. So I take 5, I divide it by 2, and I square it. So that's going to give me 25 fourths. So this is going to be 25 fourths. And then I need to multiply this 5 times that and add the opposite to the outside. So that's going to be 100 over 4, which is 25. So now that I have the perfect square in there, I can go ahead and factor it. It's going to be x minus, and this is going to be 5 halves squared, and then 12 minus 25 is minus 13. So now I'm in vertex form. So you can see putting it in vertex form is a little bit quicker than doing the other form, but again, we need to know how to do both ways. So that's how you do it when you're completing the square. All right, I just want to talk about, I'm not going to do that last one there. Sorry, I popped that up just to entice you, but I'm not going to do that. So I'm going to go back and then just real quickly talk about applications of quadratics. Applications of quadratics are a nice application of quadratics are problems that involve determining a maximum or minimum. So anytime we're trying to determine the maximum profit, maximum volume, minimum cost, anything like that, a quadratic is usually or sometimes in a lot of cases a good fit because it has a max or min, and then we can fit that to the real world situation that we're talking about. In economics, when the demand is linear, so if you're talking about supply and demand, when your demand is linear, the revenue that you create actually ends up being a quadratic. So economics is a place where you'll see quadratics applied quite a bit. Free-falling objects are classical applications of linear and quadratic functions. This formula here is very familiar to those of you who had physics, and it's something you're going to need to memorize and just be able to work with. The speed of an object can be calculated by this formula right here, and the velocity of the object can be calculated by this form right here. Okay, the t represents time. G is the acceleration due to gravity, how fast something picks up speed with just the pull of gravity. And the gravity's pull is 32 feet per second if you're talking like in feet per second, obviously, or 9.8 meters per second if you're measuring in meters. Now, if you substitute the 32 in here and then you multiply the 1/2 there, you'll notice that that's the negative 16 t squared that you're used to seeing when you're looking at objects in free fall. If you're looking at the meters per second, it'd be the negative 1/2 times the 9.8, which comes out to be what, 4.9, negative 4.9 meters per second, or t squared would be the acceleration due to gravity.